Okay, let's get started. Hello, I'm Tianyu and I'm a PhD student at Indiana University. Today, we are going to talk about our paper, Mechanized Type Safety for Gradual Information Flow. This is a joint work with my advisor, Professor Jeremy Sick. In this talk, we are going to talk about four things. In the first part, we briefly talk about why we care about gradual information flow typing. In the second part, we will introduce a definitional interpreter for GLIO. GLIO is a language with gradual information flow typing. And in the third part, we will prove type safety for GLIO in a proof assistant by following the interpreter we define in section 2. And finally, we compare existing language designs and propose future directions. In the following discussion, we will use information flow typing and security typing interchangeably. So let's dive into the first section. Why gradual information flow typing? The question is actually twofold. The first question is, why information flow typing? And the second one is, why gradual typing? To answer the first question, let's look at an example. Suppose we have an application. A user enters a string, an input string, and selected parts of the input string are sensitive. There is a web page, and the web page displays some computation results. Of course, we don't want sensitive information to get displayed on the publicly visible website. So how are we going to achieve this? One possible solution to this problem is that we can implement such an application using a security type language. A security type language regulates the flow of information, and the language enforces the confidentiality of the data. By saying confidentiality, we usually mean a property called non-interference. Non-interference says that sensitive user input data does not interfere with the publicly visible output, and the output is usually of low security. So in this example here, a high security source can never flow into a low security sink. In the language definition, you can see that the flows to operator, which is represented as a red arrow, also doubles as or operator for cast. As a result, implementing such an application using a security type language will guarantee that sensitive information stays confidential. Okay, so let's get back to the example application and consider the following user input string. The input string is constructed from three parts. In the first part, it is a first name, the second part is a last name, and the third part is a social security number. The digits of the social security number are of high security because we probably don't want a malicious party to know the actual digits of the social security number. To solve the problem of securely parsing and processing the input string, we would like to define a grammar of the input. Selected terminals in the grammar are marked as high security, which is represented as being red, and the rest of the terminals are marked as low security, which is in blue. The security annotations defined in this grammar are propagated into further processing. And thanks to non-interference, and we are implementing such an application in a security type language, high security information will not be unsafely disclosed. The other question we just proposed is why gradual typing? Gradual typing is a paradigm that bridges static typing and dynamic typing by including checks at the boundaries of statically typed and dynamically typed code fragments. A developer can either choose to put in effort to make the program type check at compile time, or the developer can leave out the annotations, the type annotations, to defer such type enforcement until runtime. Our work is based upon GLIO, and GLIO is a gradual security type language first introduced by Theorem et al. In the second section of the talk, we are going to present an interpreter for the language GLIO compared to the previous paper, where the authors choose to use denotational semantics. We find a definitional interpreter to be easier to understand, also to reason about in a proof assistant. And we are using Agda for the proof assistant here. Actually, another benefit of writing an interpreter is that we can see GLIO running in action thanks to the interpreter. Okay, so let's consider a program I'm dying. In the function application applying G to V, the variable V is bound to a high security boolean. The function G and the function F both take statically unknown label, which we write as an inverted question mark. In the body of function G, function F is applied to the variable X. And in the body of the function F, the variable X is further passed into a function publish. The function publish expects a value of low security, because the function publish displays a value onto some, say, publicly visible web page. This program I'm dying is of course well typed. So let's see how it runs. The casts serve as security checks that can capture information flow violations at runtime. So let's see the first cast. At the application side of function G, the cast is permitted since we are casting from high to unknown label. The second cast at the application side of function F is also permitted for a similar reason, since it is casting from unknown to unknown, which is also permitted. However, the third cast is rejected because the program runtime can detect that we are trying to cast a high security value to low security, which results in an information flow violation, because the information basically flows from high security to low security, which is not permitted. At this time, the execution is terminated and the information leakage is prevented. If we replace the two unknowns in the previous example, for example with static labels low, the new program MS will no longer be well typed. The type checker figures out that at the application side of function G, there is a problem since high does not subsume low. As a result, in this case, information flow control is enforced fully statically. Since GLIO is a gradual language, we can have partially annotated program M, where the program keeps the static label on F but leave out the annotation on function G, for example. Unlike its fully static counterpart, MS, M is well typed similar to I'm dying. But compared to I'm dying, the security violation is detected earlier. So let's take a closer look at how I'm runs. Similar to I'm dying, the first cast from high to unknown is successful. However, the second cast, now it is from unknown to low, fails. We know that the execution is terminated one cast earlier than I'm done, since the program is now more annotated, because we have the annotation of function f. Here we present the type signature of the interpreter, and we call the interpreter V. V takes 5 parameters and returns a result configuration when the evaluation is successful. A machine configuration is a 3-tuple that consists of a value, a store after evaluation, and a program counter label after evaluation. The interpreter takes an environment gamma, which is a mapping from variables to values, a val scope val type term m, a store called mu, which is a mapping from addresses to type value pairs. We write t, v for a type value pair. The interpreter also takes a program counter label that the evaluation starts with, and a number k called guess. The guess number decreases at each step of the evaluation, so that the interpreter says total. If we run the example program m in our interpreter, we can see that the evaluation result indeed equals to a cast error. So let's dive into section 3. In section number 3, we'll talk about the type safety. But first, we would like to explain why we care about type safety at all. We start our discussion by talking about different kinds of properties that a gradual security type language is expected to satisfy. As for a gradual security type language, there are 5 properties that we actually need to care about. Let's again consider GLIO as an example. In the previous paper, Morium et al. Have proved that GLIO satisfies non-interference, which says that the language is secure. They also proved that the gradual guarantees. The gradual guarantees say that removing annotations makes a term remain well typed, and it does not change the runtime behavior of the program. In addition to those, in our work, we also proved that GLIO satisfies type safety. Type safety says that all errors are tracked errors, and undefined behaviors will never happen. GLIO currently doesn't satisfy either blame theorem or space efficiency, so they are left for future work. A natural question is, why do we care about type safety at all? If you think about errors in a program, for example, they basically fall into 2 general categories: tracked errors, which are expected by the language designer, and untracked errors, where the program basically goes into limbo states. Untracked errors are particularly bad because they are basically undefined behaviors. A malicious party, like a hacker, can take advantage of that and basically hack the program. And it is very scary, of course. Type safety basically says that untracked errors can never occur. This is why this property is desired. So let's take a closer look at our machine model. An evaluation can result in a timeout where we run out of guess. The guess is basically the number k we just introduced. The evaluation can also throw an error. The evaluation can also return a valid machine configuration, of course. A machine configuration is a 3-tuple: a store, a value, and a program counter label after the evaluation. The program counter label can either be low or high. The theorem statement of type safety says that if the term M is well-typed, then its evaluation result after running the interpreter V is also well-typed. When typing the result, note that in the error case, the error E can only be a trapped error. A trapped error cannot be well-typed. Thus, we rule out undefined behaviors. The configuration case is straightforward. The value is well-typed, of course, and the heap is also well-typed. A well-typed heap means that the value in each cell on the heap jives with the type stored on that cell. The proof of type safety is by induction on the typing derivation of the term M. We proceed by following the branch structure of the interpreter. In the last part, we summarize 4 existing gradual security type language designs. They serve as inspirations for a new design that we briefly sketch. So we summarize the language properties of the 4 designs in a table. We can see that from the table, lambda GIF and GLIO, lambda GIF is on the first line and GLIO is on the last line. They both satisfy 3 of the 5 properties, which are the most among others. Lambda GIF lacks mutable reference, so it's not as interesting as GLIO. Instead of using gradual labels to actually classifying the data, the authors of GLIO propose to have class checking labels only, so they can prove both non-interference and the gradual guarantees, which the authors of GSLref claim that there's a tension between the 2 properties. However, GLIO doesn't do blame tracking, and it would be difficult to add blame tracking to GLIO because the class are inserted on the fly when the program runs. And the types that construct the class are stored on the heap, so they are only known at runtime. Based on our observations, we propose our vision for future language design on the next slide. So to facilitate all the 5 properties on the previous slide, we recommend that the following choices of a future language design. The first is in terms of value labeling. We prefer the approach taken by GLIO, where values must be associated with concrete labels, different from that of GSLref, which has a problem of the labels on the values becoming unknown when the program shifts to being more dynamic. Hopefully, our approach will facilitate gradual guarantees as GLIO does. But different from all existing designs, we plan to use a simple heap, so there are basically no extra information stored on the heap. And we plan also to use reference proxies to facilitate that. Hopefully, this will better facilitate defining and proving the blame theorem. We plan to include a surface language with good programmer usability, since the user does not need to mess around with, for example, inserting explicit casts by using the surface language. We compile the surface language to a cast calculus and define the semantics based on the cast calculus, similar to the path that GSLref has taken. Since both fine-grained labeling and coarse-grained labeling are the same in terms of expressiveness, we'll choose to do fine-grained labeling, similar to Lambda.js, MLJS, and JSRF. Okay, that's it for today. Thank you for your attention.